Okay, this is a bit of a sort of nerd level look, I guess, at the ROS 2000 board that's for replacing the main valve board in a Marshall JCM2000. Okay, cool. So there have been a few people who have asked a few questions about how we design things, what parts we've chosen and things like that, and I'm hoping that I'll be able to answer all the questions. So this was designed here at Keld Ampworks. It's been sold through valvetubeguitaramps.com. And it's manufactured, I should say. Oh, actually, I've got to highlight this because I like putting this in. This, although it's covered slightly by the silicon, says engineered in Nottinghamshire. So it's designed here in Nottinghamshire, and it's manufactured here in the UK as well, with a company down in Hastings. So we're not doing that little trick that people like to do, where they'll manufacture in China and then put one resistor on in their own country and then ship it out. So this is all manufactured in the UK. Hastings, and then final configuration happens either here or with Valve Tube Guitar Amps in Scarborough. Okay, cool. So I'm going to talk as much as I can in as much depth, because like I say, this is a complete nerd level video. So we'll start off, where should we start? We'll start off at this end of the board. We'll start off with component level stuff and component choice stuff. So across the board, I'll refer occasionally to this Marshall one, not because I'm particularly wanting to do a sort of comparison or shootout, but just because it makes sense to look across every now and again just to compare. So we've chosen to upgrade all of the signal resistors. So it's these blue ones here. These are metal film resistors. Metal film resistors are low noise resistors compared to your carbon resistors. And these are uprated so that we've got more than ample rating on every single resistor on this board. The anode resistor, which is your large voltage swing resistors, these are all 2 watts, and they're also rated for a higher voltage swing. Again, they're metal film, so that's all of these ones here. So I'm not sure which the anode resistors are on the Marshall board with that. I think it's those ones there. So again, so they're sort of, we made the decision to uprate them on this. Signal caps across the board, we've gone with, for all the film caps, we've gone with Weimer caps. And for all of the ceramics, we've gone with either Vichy or Murata. So that's these little ones here on all the ceramics, and then Weimer, obviously, best of the bunch on the film caps wherever possible to use them. Electrolytics-wise, we've chosen to go with Rubicons and Nippon Chemicon. I think it's all, and yeah, Rubicon, Nichicon, and Nippon Chemicon. So all really good quality Japanese brands there. Whilst I'm on the subject of capacitors, here's one that... Whoops. Whilst I'm on the subject of capacitors, here's one that people don't spot. So the original cap in what's C22 on our board, I forget the Marshall designator, is actually reverse biased in some switching modes, and so a polar cap was always fitted on the original boards, and we spotted when we were doing the sort of in-depth research on this one that actually in some switch position settings that cap was reverse biased, so that was one of the changes we had to make for reliability on this, and I don't think many people have spotted that. Okay, cool, so let's work across the board. I think the best thing to talk about over here is the DC filament supply. So the original one used an on the board all-in-one bridge rectifier part. Unfortunately, that does create quite a lot of heat, which was then transferring to board and causing some conduction issues which aren't related to the main bias thing that everybody knows about and talks about. We could have gone for another bridge rectifier and maybe just spaced it off the board, but we thought, well, maximum airflow, we'll go for 4 massively uprated discrete diodes there and give them maximum airflow around the board there. And that's proved a brilliant solution for that, because these barely create any heat now as a result of the dissipative ability they've got, which is good. Okay, let's move across. Obviously, all of these connectors are positioned in the same places or similar places to the Marshall ones, so that we've not got any long cable runs going across the board. It's probably worth talking about surface mount. So surface mount, it's one of these things that a lot of techs get a bit scared by, and unfortunately people, when they don't necessarily know how to do these things, sometimes criticise unduly. So things can go wrong if you use surface mount in tube amps. If you use them in places where they aren't capable of swinging the voltage, or in places where the pad spacing is too small for a certain voltage. I think you can see fairly clearly from looking at our board that the reason we have not, the reason that we've gone for surface mount on these is not to do with cost, because obviously, you know, we saved about, what, 6p in changing to service mount here versus doing through-hole. It's not about that at all. It's about it being the best part for the job. So there's nothing here that's swinging more than 5 volts. No, sorry, that's not true. It's nothing that's swinging more than 12 volts on the surface mount parts down here. And none of it is creating any heat. There's no heat generation in any of these components around here. Nearest one is that, but that is raised up, which we will we'll discuss in a bit. So that's why we choose to do it. We choose to do it because it's the best design for the part, not because we're trying to save any money here, because to be honest, it saves us basically no money in doing it. In fact, it probably adds in cost because it has to be run on 2 manufacturing passes. You have to do a 3-hole manufacturing pass and a surface mount manufacturing pass. So, but because this is the best way to do this circuit, and it allows us to keep the ground plane intact on the other side and various other things which result in a very low noise unit, we choose to use surface mount here, and we make that positive choice. Okay, cool. What should we talk about next? Let's move along to, I should say, yeah, so your heater trace. We talked a little bit about the heater before when we were talking about the DC filament. So we've got matching tracks on the AC part of the filament. We've got matching tracks on top and bottom, because that's the only sensible way to do it, really, to bring it along and round to the AC spade terminal inlet on this side. So that all comes through there, and that's we've then got the 2 heater balancing resistors up here, which makes a lot more sense than where they are on the Marshall board, I have to say. But we'll less said about that the better. Okay, cool. Let's move along. So I mentioned earlier that we've got, just like on the original board, we've got parts raised off the board. We chose to do this with ceramic spacers. The reason for that being that it's too often when you have the things which are just done on by a crimp in the leg, if they're shipped out and they get bent over, and then there's a potential for it to turn over and short. So since we know that we're shipping these around the world, to the States and to the East Asia and to all sorts of places where we've had lots of orders from Japan, we didn't want to have a possibility for these things to get bent over. So the ceramic spacers stop that from happening. That's why we've got these on each of the legs on the raised parts there. It should be said this was the first one off the production line, and this one had the ceramic spacers missed. This is going to be before I fit this into an amp, which I'm doing in about 30 minutes time. We're going to be putting the ceramic spacers onto this one as well. Yeah, like I said, this was from the first 12 that came out, and that was one of the things we spotted. Okay, cool. So you can see here we've used non-acetoxy silicone to secure all the caps in place. Again, this is for vibration. Now, a lot of people will make the mistake of using hot glue. That's not the way to do it. Hot glue gets brittle under heat, and it's very specifically non-acetoxy silicone, because you can actually get, if they've got acetone inside the silicone, then it reacts with the copper and causes problems down the line, and we do not want problems down the line. Okay, getting to the sort of meat of the original JCM2000 thing that we're trying to fix. So obviously this, the original problem was a bias drift going between the high voltage parts of the tube and the grids of the tube. So this is why we have slots in the PCB here between the pins, and also the traces. As soon as they come off the pin, your negative bias voltage is taken off in one direction, your HT is taken off on the other one. So there's huge spacing across the board between those 2 points. You might ask, why is there no slot between these 2 pins? So this is the screen grid pin, this is the anode pin. The reason for that is because there doesn't need to be. There's basically no voltage differential between your screen grid and your anode that makes any at all worth talking about. If you have a large voltage differential between those 2 pins, then something else is wrong. and that's not going to do anything to save it. So that's what we've got there. This fixes the bias drift entirely. We've done extensive tests in terms of heating up the board around these areas to make sure that doesn't come back, even in really quite extreme heat conditions. Okay, so the next thing that we've done, which is again on the same principle, so that we do not have to have crossing over the HT line and the bias, we've chosen to take the HT line between the outer valves. We've chosen to take it via an external wire link. There's a couple of reasons for that. One is so that we keep it well away from the bias network, and we don't mind adding that extra bit of manufacturing and labour in if it keeps it reliable. And the other thing is it doesn't break the ground plane, which is something I'm going to talk about in a minute. It's another nice controversial thing that I want to wade in on. Okay, cool. So we talked about that. Let's flip the board and have a look. So this is the board on the other side. The masking tape still on from the manufacturing process here. As you can see, we run a ground plane across the whole of the back of the board, and all the purists say no, do not do it. And obviously, if you were to look at the original Marshall one, you wouldn't see a ground plane there. Okay, so the reason we do a ground plane is simply because it's better, and it's quieter. And the proof is in the pudding when you install one of these and you find out that it is quieter. There are a lot of people who will say that it creates more noise, that it causes traces that can induct noise into the ground plane and thus propagate into the preamp. That's simply a product of how well you design your PCB. If you do not design your PCB well, you do not give sufficient isolation between radiating parts and parts that require immunity from radiated sources, then you're going to have problems. But if you do it properly, then you do not. And if you have a ground plane, then you lower your microphonic your radio frequency interference issues. You lower your electrostatic interference issues as well. I mean, I've done, not specifically on this board, but I've spent large amounts of my career looking at how audio products are affected by electromagnetic interference, and every time the ground plane makes it better, every single time. Okay, cool. So that's that. I think we've covered everything I wanted to say. Like I said, this is complete nerd level. I think we're on 13 minutes. One other thing that I didn't mention, we've upgraded the screen grid resistors across all of these here. The simple reason for that is that modern valves are not always that robust in their screen grid performance, and you can quite easily increase the screen grid value without any real effect in performance of the valves, but it does mean that they last a bit longer. So that's good. Oh, flyback diodes, there you go. I hadn't put that in my notes, but we've also added flyback diodes on the anodes of both of the, so that's this one here. So they are protecting your output transformer. I'm just going to have a last scan round to make sure that there is nothing else that I want to discuss before I finish this. Hopefully it's answered any questions. Obviously, if there are any questions, do just leave a question in the comments. I think we're probably going to pop this up on YouTube. Leave a question and we'll definitely answer it.